our last part of photogrammetry is about our last type of photogrammetry. If you guys remember back in time when I discussed with you photogrammetry or introduced for you photogrammetry, I said we have options. Option number one is to hold our camera and take photos while the camera is handheld or maybe set on a tripod for a better image. But that's called close range. Close range. So I'm very, very close to my object. Then the second option is to fly our camera, put it on a moving platform, including drones and aircraft. Okay. But in this case, even if we have aircraft, then we can fly maybe a couple of kilometers or 3 kilometers above ground. What is our final stage? Simply is satellite. So you guys know that satellite mission is something that has been around right now probably for more than 60 years. So I think back in 1950s or 60s, that was the invention of computers and do precise calculations. And then satellite mission was very hot topic. So everyone was to go to the moon and simply, send some satellites in the space. Even until now, you guys heard about Elon Musk is sending, those satellites like lots of them to simply broadcast internet signals to get internet on a very wide, large scale, on a very, very cheap. I think everybody now heard about this. So before I started the discussion about satellite photogrammetry, I just want to remind you that when it comes to the satellite system, there are so many satellites in the sky to the point that astronomers, they become very concerned that they can they occlude the space object. Okay, so satellites are simply, in my view, are split into different categories based on their use. So I'm going to show you here a few of them. I'm not aware of all of them, but I know some of them. So number one is communication satellites. The one they are used for example, internet signal, or maybe for channels. Like sometimes you can see a channel based on satellite. You have a plate, like a satellite plate or dish, and you can simply receive a signal. Those are geostationary. And I want to be clear about the word geostationary. Geostationary, it means stays above one location. I'm sorry, I have like a typo error. So they stays above one location. For example, it fly in the space, it stays above Alberta forever. And it's not really static. It just goes with the same speed of the Earth rotation. So they move with the same speed. So relatively, they look the same on the same spot. That's called geostationary. And again, for the purpose, if you want to have, for example, a movie, and then you have a satellite dish, you think your satellite dish will move all the time or should move all the time? It shouldn't, huh? And that's why those kind of satellites, they are geostationary. You just have to orient your dish in one direction in space, and you can get the signal all the time. Same as weather satellites. Weather satellites, although weather satellites, they don't provide any signal for us, but they stays above, for example, Alberta all the time. Because from weather satellites, we can take photos and we can predict the movement of the clouds, and we can simply do some kind of forecast for the weather. So those are also geostationary. There is one satellite group of satellites, which you guys know and aware of. Did you guys learn in last year about GNSS or GPS? I think you did. So what do we call these satellites? Which category they fall? They fall under navigation satellites. A satellite, which is the purpose of these satellites, is to rotate around the Earth. And why they rotate? To simply provide a continuous coverage on the Earth, everywhere, anywhere on the Earth, 24/7. And that's why they rotate. So those are not geostationary. They rotate around the Earth, but they are not sun synchronized. And I know some of you will say, okay, what does it mean sun synchronized? Please wait for a minute. So our last group of satellites in this slide, which this is our focus, for the rest of the today lecture is something called EOS. EOS, and EOS stands for Earth Observing Satellites. Okay, and what they do is, again, those are different group of satellites. Their objective is to rotate around the Earth. So they still rotate, not geostationary. They rotate, orbit around the Earth. However, the design has some sensor like cameras where they take some images of the Earth and send the images to the Earth through the signal. Now I'm asking you, when we say here sun synchronized, what does it mean? It means my satellite is following the sun. Where the sun goes, my satellite will go. And obviously, for obvious reason, because simply, can I take photo in a dark room? Doesn't make any sense. It will be dark. So which means, for example, right now, we are in Calgary. It is sunny and lovely outside. However, in Egypt right now, it's nighttime. So for sure, my satellite is not going to take a picture of Egypt right now. The orbit of these satellites are sun synchronized, and because simply they follow the sun, because we need to take a photo with some enough lighting. While navigation satellite, GPS or GNSS, not necessarily they have to be sun synchronized. They have no business with the sun. They provide 24/7 coverage. Okay. Now let's move on. As I said, we have so many satellites, even from GPS. Those guys here right now, I think, if I remember correctly, we have roughly about 135 satellites for navigation only. For navigation, it means including GPS, GLONASS, Galileo, Jibo, like every country almost, they have their own navigation system. Whether it's complete or incomplete, it's on their way. So we're getting more and more satellites in the space. Okay, and from this system here, from those, we have so many, and I will introduce for you guys some of them in today's class. Now I'll give you kind of a little bit of history, and please don't get bored. I'll give you some history about, the evolution of those systems. I will try to be as short as I can. I'm gonna provide you the first one and the last one, and in between, that is up to you. So the first satellite system, there was a program for Earth resources satellites that was started in 1966. And the goal was to cover and gather remote sensing data about the Earth. Remote sensing data about the Earth, which is images. So the first satellite called Landsat-1, the name of the first system, it's Landsat-1, launched back in 1972. So that was before I was born, okay, back in 1972. Almost 1 year before I was born. Okay, so in 1974, Landsat number 1 transmitted 100,000 images of the Earth, covering about 75% of the Earth. I can't forget to mention what is kind of advantage you get when you have a camera on satellite. Can anybody tell me right away what is the biggest advantage when you have a camera on a satellite that flies few hundred kilometers above the Earth? Any thoughts? What kind of advantage? Did we discuss in our class here, the farther you go with your camera, you cover, a single image will cover more area? Did we say that?
Yes.
Okay, so you guys can imagine now when I fly, I have a camera on board of a satellite. You can think about it that every single image can cover maybe 20, 30, sometimes even 180 kilometer on the ground. So maybe one satellite image can cover maybe 4 or 5 cities like size of Calgary. Okay, so that's the big advantage, that we get global coverage rather than a drone photo that simply covers maybe 30 meter by 30 meter on the ground. Okay. Now, one of the things that kind of for the record, that because of Landsat number 1, we discovered, we're able back in 1976, we're able to discover a small tiny island 20 kilometer east of Canada. Okay, again, you're flying very high, so your image will capture remote things. Okay. Landsat 7 was simply taken out of service back in 1978, but since then they keep sending several missions. So I can tell you, this Landsat number 1, do you know what is the version of Landsat number right now? We have Landsat 8TM. So we have Landsat 2, 3, 4, 5, 6, 7, 8, and 8TM. Okay. Now I want to take you about, something that you will understand shortly, something called ground resolution. So 1 pixel of Landsat 1 covered on the ground 80 meter, 80 meter. Okay. So if the pixel covers 80 meter by 80 meter, guess what? You cannot see a house. Your house, which is maybe a 10 by 10 or 10 by 12, okay, you cannot see this on this image because a pixel covers 80 by 80. So you need 8 houses. No, sorry, not 8 houses. You need about 16 houses. No, I don't know. It's 8 by 8. Yeah, I need 64 houses next to each other so you can see them in 1 pixel. Okay. So anyway, those are kind of course resolution in 2021. What is the system that is the recent one? So here we have World 4 View, World View 4, and was launched in 2016, and the resolution is 31 centimeter. So you can see we went from 80 meter to 31 centimeter. You can see lots of development there. So which means on this 2021 image, I can identify my own house on this 31 by 31 centimeter. Now, I need to get you ready. In order for you to understand the different system, every system comes with characteristic, with some specification. And my objective within the next maybe 20 or 30 minutes in this class, I will try to introduce for you the meaning of those terminologies. For example, when you hear a word called GSD, GSD. So what exactly GSD stands for, I will do that for you. I will try to teach you what does it mean GSD. And remember, once you understand all those meaning and terminology and characteristics, ultimately you should be able to pick one of the system on top of other systems. So if I give you, for example, 5 images coming from 5 different satellites, it depends on your application. You should be able to pick one of them and say, okay, you know what? This is the one I'm going to use. This one will serve me better. Let's get started here. So my first topic for you here is something called ground sampling distance. We typically use GSD. And in simple term, it's called ground resolution or spatial resolution. Simply, it's how much every pixel on your image covers on the ground. You guys remember, huh? A digital image, it is built out of small pixels. Next to each other, make an array or matrix of pixels, okay? Kind of row and column. So this is very, very nice slide here. It shows you the variation of the GSD, and you also can identify your features. Let's get started here on the bottom right corner. So the bottom right corner, it is the highest resolution where every pixel covers 0.01. So my GSD here is 0.01. It means every pixel covers 1 centimeter by 1 centimeter. And you can see everything is clear. I can even see the side mirror of my car. It's very detailed. When you start losing or reducing the resolution, it means the number gets bigger. So here 0.03 and 0.05 and then a 10 centimeter. What you see happens here along this line. I'm going from the right to the left. You see what's happening, huh? You see what's happening? You see we're losing details. My resolution gets coarser and I'm losing details. All the way until I go to this resolution here and I'm asking you at 40 centimeter, are you able to identify that this is a car?
No.
No, huh? You can see I'm increasing my ground sampling distance and then I'm losing details. But so you know, not every single application I need to see the car. If I'm using satellite image to count the number of cars on the road, yes, okay? If I want to use satellite image to count the traffic density on the road, then for sure I need this kind of image. But I'm asking you, if I, for example, want to monitor the expansion of Calgary over the next 20 years, okay, so I'm talking about different application. I'm trying to monitor the expansion of Calgary over the next 20 years. Do you think I really need a 1 centimeter resolution like this one?
No.
No, absolutely no. Remember, the expansion is measured by the extent of the houses. So we're building new communities on the north and the south. And for sure, even 1.6 centimeters is too much for me. Okay. So you get the idea. So for now, I want everyone to understand the meaning of GSD. Let's move on to next one. And to be honest, I would like to apologize. So if you're bothered by this discussion, okay, please just enjoy. Huh? So this discussion is pure physics discussion. Pure. Okay, you will see. Probably you guys somewhere in your courses you learn about electromagnetic waves. Can I get some confirmation? Anyone in my class learn about electromagnetic waves somewhere along your study? Electromagnetic waves. Okay, thank you, Matthew. Okay, great. So electromagnetic waves, those are spectrum. There are so many of them, and all of them, they travel at the speed of light, which is 3 times 10 to the power 8 meter per second. So all of them, they share the same speed. However, they vary in wavelength and frequency. So there are some electromagnetic wave that they have a very small, very, very short wavelength. When the wavelength is short, what happens to the frequency? Any help? When the wavelength is so tiny, what happens to the frequency?
Does it increase it?
It increases. And if the frequency is very high, what happens to the energy in this signal? Any help? Anyway,
Does
you
it
know what?
increase?
I'm go ahead. Sorry. Go ahead. Sorry. Go
I'm
ahead.
just guessing that it increases. I don't know.
It increased like crazy. Okay, so that's why what happens here when the wavelength is short, the frequency is high and the energy is so high. And that's why here on the very, very short wavelength, we have gamma rays. Watch this. We have gamma rays. Do you guys know what triggers gamma rays? Any general knowledge? What triggers gamma rays?
Isn't that like nuclear stuff?
Exactly. So gamma rays are triggered by nuclear reaction. Even the sun, in the sun, there are lots of nuclear reaction. So for sure, there is a gamma rays. Gamma rays are super dangerous. They are not. I cannot say dangerous to be honest. I can say lethal. So if you are exposed to gamma rays, you will die immediately. Okay, unless you are Iron Man, huh? But you will die immediately. Now, next on the spectrum, we have X-rays, and X-rays also, they have a short wavelength, they have high frequency, and they are not really good because simply X-rays, although they are powerful, they can penetrate our bones and we can take pictures with them for our bone fracture, but you are not supposed to wake every morning and get some X-ray. You know that, huh? If you get more X-rays, you know what happens. You could end up getting cancer, okay? God forbid. But anyway, so the second one is X-rays. And again, if you go along the spectrum, we change the wavelength, we get different characteristics of the wave. Really, what's important for me here, couple of things. Number one is visible light. So visible light is part of the electromagnetic waves, and the wavelength is between zero point 0.4 to 0.7 micrometer. 0.4 to zero point 0.7. I always remember this number. I don't know why, but it's between 0.4 to 0.7. And you can see here we have the red. So the red is simply 0.7 micrometer, while the blue is simply zero point 0.4 micrometer. And you can see we have the green and yellow, but basically RGB, huh? Red, green, blue. Those are the main colors from zero point 0.4 to zero point 0.7. And by the way, so you know, the word 0.4 to 0.7 in physics called band, spectral band. So between 0.4 to 0.7, we call spectral band, okay? Now, really what's important for me also is something called infrared. And infrared is something, the wavelength is more than the visible light. You cannot see it with your own eyes, but your skin will feel it. If you stand in the sun, your skin will feel the infrared because it has thermal effect. Okay, it has thermal effect. Now, why Tahir is spending this time in a surveying class about this kind of physics discussion? Here we go. Here is the reason. So, guys, here is a fact. Every time an energy hits an object, two things will happen. Two things will happen. The object will absorb some of the energy. That's fact number one. Fact number two, the object will reflect some of the energy. For example, if I hit my My object with 100 unit energy, my object maybe will absorb 30 and will reflect 70, okay? So, and by the way, the reflectance is a signature, just like your signature of your finger. And what does it mean? It means every material has its own reflectance, okay? And from the reflectance value, we're able to identify the type of the material. Now, this reflectance is not constant. For example, let's say I have a black ball. Does this black ball always reflect 70% of the energy? That's not true. So the reflectance amount, it is based on the wavelength. So it depends on the wavelength. And that's why if you try to draw a relationship between the wavelength and the reflectance amount, it will vary up and down, up and down. Now, let me ask you a question. Let's assume that in this picture here, we have three different material: soil, and we have a dry vegetation, and we have a green vegetation. Okay, you can see them by different line type. If you take a photo of one area on the earth in a visible light, so remember, visible light is from 0.4 to 0.7. So this kind of blue here, this rectangle here is your visible light band. You can see in the visible light all the curves. You can see all the curves, they are very close. While if you take a picture of the same scene using infrared camera, do you see where is the green vegetation? Up here. And where is the dry vegetation? It's down here. So you can see there is a huge difference. And this huge difference allows us to differentiate between those. Did you guys learn with the Milan? I'm not sure. Yeah, I know because of the online. So when we used to have a classes, Milan in the like building science course used to have an infrared camera. Anyone learn about infrared camera or use infrared camera? Or have seen or learned about infrared camera? So, okay, perfect. So infrared camera is a camera that has a sensor, but this sensor senses the energy not within the visible light band from 0.4 to 0.7, but goes beyond this limit. Okay, so different band. And Ryan, can you please help me? What is the use of infrared camera? Do you know what is the use of infrared camera? It has so many uses, by the way. Do you know?
Change in heat, doesn't it?
Say it again, please.
Am I thinking of something different, but doesn't it check to change in heat?
Yes, so yes, you know, this one here, it is used to for heat. Like if you have an old house and the house leaks some energy, yeah, and typically the leak happens around the window. So you can simply, if you go in a one cold day and then point your infrared camera into the building, you know what happens? You will see a red. And by the way, so you know, the picture of the infrared camera doesn't look like the image taken by a normal sensor, like a normal camera. When things are hot, it looks like it's red on your infrared camera, okay? But it doesn't look like a real image. Anyway, my point is, without going into so many details, when we take a picture in different band, different than the visible light, we get lots of information because simply we can see things very different in an infrared image, okay? One of the application, for example, is to look at a field. When you look at fields and you have some vegetation which watered or rinsed, then it looks like this. While if you have a dry vegetation which is stressed, need to be watered, it will look completely different. And that's why we can use our satellite image to collect some remote sensing information about the object. Anyway, so one thing also is about revisit time. We already said that EOS satellites, they are not geostationary, yeah? They are not in the same place. What they do is they turn and orbit around the Earth, same as GPS satellites. And since this is happening, it comes back to the same spot every specific frequency. Watch this. So in this picture here, where is Egypt? So Egypt is here, okay? So my satellite is roughly, let's say, above Egypt, and it will take an image right now. And it's going to rotate around the Earth. It will come back above Egypt one more time, probably in 1 or 2 or 3 days. That's called revisit time. Now, the question is, revisit time, is that something I need to know for my satellite system or something it's irrelevant? I don't care whether it comes every day or every 20 days or every month. It matters. Why it matters? It matters only if I'm studying a dynamic phenomena, a phenomena that changes every day. So if I have a phenomena that changes every day, like for example, like the tsunami or oil spill, what happens? I need a system that gives me an image over the same area very frequently, every day, for example. However, some other application, we don't care. As I said, if you work for the city of Calgary and they ask you to pick one satellite system to monitor the expansion of Calgary over the next 20 years, I'm asking you, would you care about the revisit time? What do you think? Would you care about revisit time at all?
Yes.
Okay, so you think revisit time, like a Calgary expansion, does it happen overnight, or it takes months until you get some increase or expansion of your city?
It would tell you the intervals of your pictures, but like I guess that's not relevant if it's happening over 30 years.
Yeah, you know what? It happens. Let's say we get every year, so we maybe build some more houses. So really, it's not going to happen overnight. And I can tell you the range for satellite systems, the range between 1 day to 16 days. So the fastest it goes every day, it comes back every day, and the slowest it comes back every 16 days. I think it doesn't matter because even the worst or maybe the slowest, it comes every 16 days. And in 16 days, would you build the house in 16 days? A single house in 16 days? Not really, huh? So anyway, if you monitor the expansion of Calgary over the next 20 years, I don't think you need anything like it's irrelevant. It doesn't matter. Maybe you have some other criteria when you simply look at this application. Now, one more technical term that I want to teach you. So far I taught you the following. I taught you GSD. I taught you spectral band. I taught you the revisit time. The next one is called swath width. And if you remember, we kind of learned about this one, but it's not satellites. It was about Civil 3D. Civil 3D, huh? When I'm trying to cut sections through the ground, the software asks me, how much is your left swath width? How much is your right swath width? So in satellite imagery, what does it mean satellite width? And I need to give you kind of a background. You know what? In your camera, if you have a camera, or even in your cell phone, your camera is a frame camera, which means the sensor looks like a square or rectangle. So the arrays of those small elements are arranged in a kind of matrix, like row and column. This is not the case for satellite system. In satellite system, they have a linear array, not 2D, huh? So the film or the light sensitive element is not 2D, it's only 1D, kind of a line. And what this happens, simply, it takes kind of an image, like only a line, and then the satellite is moving this way. I watch this. So the satellite is moving this way. And remember, we are only at one image. We're covering only one strip like this. I watch this. So from here to there, to there, to there, to there. You can see this is a line image, huh? A line image, like let's say in yellow. Remember, the satellite is in motion. So what it does, it kind of push broom, huh? It kind of push broom. It sweeps the earth. And that's why the satellite image, the width is constant, is simply, let's say, 35 kilometers, while the length of the image is like a carpet, huh? Like a runner carpet. It goes forever. So the length, which is this direction here, it goes forever. Because again, it's kind of a line array, line camera, and as you move your system, it will simply survey the next line. I'm gonna try to show you, so it will survey the next line and so on, so it's kind of like push broom camera. So the swath width is simply the width of your image, but the length is, you can ask for any length, but the width is constant. So what happens here in the next after a few hours, the satellite will shift, will simply go here and cover the next line, and after a few hours will cover the next line, and that's why it simply covers the entire Earth. So kind of the orbit will shift as you go. Now, swath width, is it something that I need to think about it, or something I don't care about it? For example, if one system give me a 10 kilometer, Another system gave me 185 kilometer. I'll tell you the trick, huh? Let's think about Calgary. Anybody knows roughly, roughly the size of Calgary? Roughly, huh? Not with a millimeter, just with kilometer. I'm good with kilometer. Is it 10 kilometer by 10 kilometer, or 20 by 20, or 50 by 50? Any smart guess? Any smart guess the size of Calgary? Is it 50 by 50, 40 by 40? You don't have to be very precise. I need to get your feeling, huh? Is it 10 kilometer by 10 kilometer, or 50 by 50?
50 by
somewhere
50.
in the middle.
It's a 50. It's roughly 50 by 50 kilometers. So if you go east to west and north to south, probably it's 50 by 50. Now, what does this mean? It has to connect with our discussion here. So I'm telling you, what happens if this dimension, which is swath width, let's say this is 10 kilometer, huh? Let's say this is 10 kilometer. I'm asking you to cover Calgary. How many images I need to stitch together? If this is 10 kilometer, the width of my swath width is 10 kilometer, and I need to cover Calgary, entire Calgary. I'm asking you, how many images do I need to stitch side by side to cover Calgary?
More than 10.
Looks like we need 5. Huh? So we want 10 kilometer plus 10 plus 10 plus 10. So it looks like we need 5 strips, huh? 5 different images. And some of you will say, why not? Some of you will say, why not? Let's buy, 10 images and stitch them. 5 images, stitch them together. The thing is, when you stitch images together, it has some trouble that comes with those stitching process. Number one, you must have ground control point. Number two, there will be some change in lighting. Huh? So the illumination, the sun angle will be different. That's why the images will not be consistent. Some of them will be darker, some of them will be lighter. And it doesn't look great, so you have to make a filter. So you have to attach them together, then make a filter to have a consistent lighting, okay? I'm not sure if you guys follow this discussion. I kind of understand it's not easy, but I need some help, huh? Are you guys following what do I mean? If we need to stitch multiple images side by side, number one, I need control point on the ground. Number two, the light will be different because of the sun, huh? Remember, those images are taken at different time of the day, which means they will have different light condition, which means I need, after I stitch them, I need to pass a filter so you will have kind of uniform look of your image. Are you following, or this is a very difficult discussion?
We're following.
Okay, so anyway, stitching is not fun. That's what the bottom line. If you haven't followed the discussion, stitching is not fun. And that's why if you have one project that has a wide coverage, probably you want to pick one satellite system that has a larger swath width. If you have a larger swath width, it means you don't have to go through the pain of stitching. Okay? Now, look at the next one. If you didn't like this discussion or this discussion here, then look at the next one. The next one is pure computer discussion, pure, okay? And it's about quantization on how we record a digital image. This is something, by the way, you as a user, probably you've seen 100 images on Facebook and 100 images on your machine, but you never bother to learn or to worry about how these images are stored in the computer memory, okay? So I'm going to share with you how these images are stored in computer memory. And for simplicity, I will use black and white. And the same discussion applies for color image, okay? Because color image is nothing more than 3 images on top of each other, a red and green RGB, huh? Red, green, and blue. Any color image, it has 3 layers, a layer for red, a layer for green, a layer for blue. But again, the discussion is good enough, huh? So let's talk about black and white. So in black and white, we have black point, like black element, like this one here, and we have bright element like here. So how do we store this image on the computer? Number one, you have to understand that the element that can create this image called the pixel. Pixel. So a pixel simply, it's a degree of gray, and the way we store this pixel, we simply store it as a number. You can see my top left corner of my image, top left corner, it's a pixel, and on the computer storage, I store it as a number. Huh? Look at this. So you can see, let's say I have 18, and 11. So the image will convert it into a number. But the thing is, when you convert your image into a number, It comes with a scale. You know what? If you don't follow the meaning of a scale, watch this. I'll give you an example from our class. Midterm is coming, midterm is coming. And when I mark the midterm, I will assign every one of you a mark, a grade, between 0 to 100, correct? 0 to 100. But some other instructor can mark your exam from 0 to 10. And some other exams, they can mark from 0 to 5. And remember, you guys are the same, but we're marking your exam depending on different scale. So in computer, we have something called 8-bit scale, 8-bit, and you can see it's here. And again, if you study computer somewhere in your classes, you know what does mean 8-bit image, 8-bit scale. So 2 to the power 8, if you right now do 2 to the power 8 on your calculator, you will get 256. You can see here, 2 to the power 8 is simply 256 degrees of gray. 2 to the power 8, because it's 8-bit, it's simply 256 degrees of gray. And what happens here is that we will assign numbers for every pixel, range from 0 to 155, where 0 is black, or 0 means black, and then 255, it means white. How about in between? For example, 15 and 18 and 20, all these numbers, they will be a different level of gray. Please look at my screen and you will see the variation of the level of gray. How about 11-bit image? 11-bit image, same idea. 11-bit image, it means I'm recording my image on scale 2 to the power 11, which is 2048 level of gray. Now we can see there is a shift one. Look at this. So here 256, and all of a sudden went to 255. Anybody knows the secret? Like if you multiply 2 to the power 8, you will get here 256 level of grays. Why all of a sudden I showed here 255? And why here 2048? And here the white would be 2047. The answer is very simple, because we're not starting from 1, we're starting from 0. Okay? So it means we start for counting from 0. And if you count 0, it means from 0 to 255, you already got your 256 level of gray. Anyway, bottom line is we can store our image on a different scale. Let me ask you, which one is better? To store my image on 8-bit scale or 11-bit scale? And if you don't follow the discussion, let me ask you, if you have the option to tell me, Tahir, mark my exam from 100 or from 10, which one you choose? What do you think? Or it doesn't matter? If you have the option to ask me, Tahir, mark my midterm exam based on 100, like give me a number from 0 to 100, or someone will say, okay, give me my mark from 0 to 10. What do you think? Which one do you think is better?
100.
Yeah, on a scale of 100, because on a scale of 100, I can see more details. I can give you 96, 97, 91, but on a scale 1 to 10, maybe I'll give you 0, 1, 2, 3, 4, or maybe 10.5, sorry, 9.5 or 8.5. So you can see when I increase my scale, then I see more details. And that's exactly what's happening here. When we store our image on 11-bit scale, we simply can see more difference in gray level. However, this is kind of a confined statement, is not absolute statement, because simply when we look at an image using our eyes, like me and you will absolutely see no difference between 8-bit and 11-bit. So if you save your image as 11-bit, or you save the same image as 8-bit, you as human will not see the difference. Can you please answer me? I need some help. Okay, I need some help. Can anybody help me to tell me the difference between my cursor? I'm going to move my cursor here, and please tell me as soon as you see different level of gray. I'm going to go from the far left. I'll move it slowly. Once you see a difference in gray, shout, please. Hello. I'm going from left, so this is black, and I'm moving slowly to the right.
Probably right after 8.
Yeah, you can start seeing. My point is, our human eyes, we cannot see more than 60 to 70 degrees of gray. Our human eyes. So even I store my image on 11-bit scale, I don't see any difference. It's the same. However, who can see the difference? Computers, right? Because computers will see the difference between 11 and 10, while you cannot see the difference between the gray level by 10 and gray level by 11. Okay, so this is fantastic. The 11-bit scale is fantastic when I do the interpretation using computer, while if the interpretation is done using human eyes, it doesn't matter. I need to remind you that if you store your image 11-bit scale, it requires more storage. It requires more storage. So it will take, for example, a 10 megabyte, while if I store it on 11 at 8-bit scale, maybe it will take 6 or 7. So it requires more storage. Now here is my last slide, and I'm hoping that I was not so super heavy. This last slide, to be honest, I'm not gonna go spend more time because you already know all the juice, You know all the terminologies. So if I show you this one here, which is a table that make a comparison between 1, 2, 3, and 4 different satellite systems. So those are satellite systems, and we call them Iconos or Spot 5 or even QuickBird or Landsat 7. Those are different satellite mission. Every mission or every sensor, it comes with characteristics. Okay, for example, watch this. So those are the characteristics of Iconos. For example, it produces for you an image with a ground sampling distance or resolution of 0.8 meter. Okay. It gives you some spectral bands of visible light. So you can see here we have visible light, red, green, blue. And also it gives you a infrared channel, okay? Revisit time is 3 days. So it comes back to the same spot every 3 days. The width of the swath is 11.3 kilometer. And then finally the quantization is, it records the image on 11-bit scale, okay? And you can see, you can compare this one against Spot 5. Numbers are different. Now, for example, let me ask you, I'll give you an example of how can we use all the knowledge that we learned so far in my class to pick one satellite system that simply serves you the best. For example, let's say I'm working on a project and there is a tsunami or oil spill, and I want to monitor the change of the oil spill. And remember, oil spill, the main criteria here is that it's a dynamic phenomena where it changes very frequently. So among those systems, you think I'm going to choose Landsat 7, where it has 16 days of revisit time?
No.
No, that's very, very slow. It's 16 times. Now, some of you will say, what does it mean 2 minus 3? Remember, this is not 2 minus 3. This is a range. So you'll get an image on the same location between 2 to 3 days. How about this Spot QuickBird? It is between 1 day to 3.5 days. And I know some of you will tell me, what does it mean range? Why sometimes I can get image every 1 day and sometimes I get every 3.5 days? It depends on where you are on the Earth. If you are close to the equator, then the satellite goes there very frequently, so you get image every day. If you are very north, like close to the North Pole, in this case, the satellite doesn't go very often, which makes sense, Who wants to buy satellite image on the North Pole very quickly, Nobody. So that's why it goes there every 3.5 days. One thing I want to mention, those satellite systems, they don't collect data all the time. They don't. Otherwise, it's a waste of time. So I think they have kind of a frequent, let's say, every few months, they will collect some photos. And also, they can collect on demand. So if you want to order some photos or images, you can order from the archive, something that was collected in the past, or you can pre-order something that is going to happen tomorrow. Okay? And there is a minimum order. But again, this is a different discussion. I don't want to flood your brain with so much information. This is completely different domain, satellite images. Okay, so for example, if you want to order, it has minimum order, and like let's say minimum $2,000, and so on and so forth. I'm hoping I gave you kind of a little bit of idea about satellite images, and we still have 3 minutes for questions. Please go ahead if you have any question for me. Not a single one?
Taher?
Go ahead.
About the satellites, do they overlap or not?
Yes, they do, sir. Yes, they do. And by the way, they can also tilt the sensor. So sometimes they can tilt the sensor forward and you tilt the sensor backward, and this will give you a stereo vision, huh? Probably I'm thinking that you're asking about stereo, huh? Stereo, creating a stereo like a 3D from satellite image. Are you?
Yes.
So to answer the question, yes, there is an overlap. There is an overlap between the path of the satellite, so you get overlap on the ground. More importantly is the sensor can simply lean forward. I'm going to show you the picture, huh? So I'm going to go back to my slides here. Look at this. So simply the sensor, it can be tilted forward or backward or at the nadir. It depends on the request, huh? If somebody requested some tilted photos, and remember, the more you tilt, you get better XYZ. If you just take a vertical photo, doesn't give you a good idea, good accuracy for the XYZ. Any other questions?
Why do we care about 11-bit images if we can't tell the difference between?
Because right now the interpretation of those images is never done by the human right now, never. Right now in 2021, the interpretation of the image to tell, for example, this is a stressed vegetation, or this is corn, or this, all these kind of questions, it is done by the computer, and the computer will know the difference between 10 and 11, although you as human cannot see the difference between 10 and 11 gray level. Does it make sense?
Yes, thank you.
Any other question? Thank you so much. Amazing class. Thank you so much. We'll see you guys again. Remember, tomorrow, I think between 6 to 7, please check the email. I will be online. I will send you probably right away an invitation for this session. If you have a question, please come. If you have no question, then you are free to come or not to come. So there is no obligation. Huh? It is not a review session. It is just Q&A if you have any question. Thank you so much and have a wonderful day.
Thank you.
Thank you.
Thanks. You as well.